Okay, so I assume I'm good to go and everyone can see the slides. Uh, my name is Joe Sedlars. I work for a small startup by the name of Gigantor. Gigantor incorporated in 2020. Uh, Two of the inventors are former Microsoft guys. I think one of our inventors is Microsoft employee number 14. But we're incorporated in Melbourne Beach, Florida. And we have just a very specific piece of a technology that just very privileged to talk to you about today. So thank you all very much for allowing us this opportunity to talk with you all. So just to get started, and very specifically, I'll draw your attention to the upper right corner, where our company Gigantor has created a patented technology that we call Gigamax. And what we do is we conveniently convert neural network models into parallel pipeline circuits. And the result of doing that is an astounding increase in speed, near zero latency, and essentially the maximum computational efficiency that you can get out of a piece of silicon. That's quite a claim, I know, and I'll explain that a little bit. But the first thing to get your head around when we talk about this is that we are a non-von Neumann architecture. And what that means is we are not a processor, right? So on the left, if you look at a GPU, a TPU, or a CPU, those all use a von Neumann architecture, a computer architecture that's been in existence for about 70 years. And it's an architecture where you have a compute node that goes off, grabs a piece of data from memory, brings that piece of data back into the compute node, and performs an operation on that piece of data. So operations per second or so forth is a logical measure of performance in a processor. But going off chip and grabbing data and bringing it back usually takes quite a lot of time. And most computer scientists that I've spoke to tell you that it would consume at least 50% of the total power that you're using to process your model or your program. In our case, on the right, we're not using that fetching process, right? What we're doing is we're taking every node and every layer in a neural network model, and we're hard coding it into a circuit. And by doing that, we avoid all of those fetching operations, and only the data streaming from the processor, moving through the circuit, that's the only data that's in flight. And so by doing that, we eliminate that whole classic von Neumann architecture. We also eliminate the need for RAM. So you no longer need a stick of RAM in order to process your machine learning algorithm. And what we say is that the performance of this circuit is predetermined, or we say it's deterministic. And so what's interesting about this is you tell us how fast you want to go, how many frames per second, what your latency is. You give us a model, and we'll build the circuit to reach that performance, right? In a von Neumann architecture, performance is always a variable. So as you increase the workload, the performance is naturally going to decrease, right? So as you take a heavy truck and you begin to drive it uphill, that performance is going to decrease. That does not happen in a circuit form. In a circuit form, the performance always remains the same, right? No matter what your workload is, that performance is predetermined before you even build the circuit. And so you can have, as we say, the absolute maximum computational efficiency that physics will allow. And so we work at the rate of the sensor input. We can do high definition images, 4K, at 480 frames per second, or in fact, at any speed you like. And so the animation that we have sort of going here on the left and right is when you're working in a GPU, whether that's a Jetson or any other type of small GPU or large GPU, you have to ingest the whole frame typically in one one full ingest, and then you perform the computation on that frame. And then the next frame you grab might be 3 or 4 or 5 frames down the line, or more. Not so in our circuit form on the right. What we do is we ingest pixels, and by the time you get just enough pixels to do that first 3 by 3 convolutional layer, we perform a calculation, and then we're on to the next frame, the next 3 by 3. And so what happens is by the time you get done with the first frame, you're already microseconds away from completing the second frame. So it's really an astounding way of doing a pipeline parallel process. So again, not a processor, but a hardwired circuit. And by doing that, we get efficiencies and speed and latency and so forth. And so I'll just say on this slide that we are fully patented. We have about 3 patents that have already been approved in less than a year, and working on our 4th and beginning our 5th patent. And so the first patent deals with this idea of a parallel pipeline, where each node, each layer has its own dedicated circuit, avoiding any shared resources, right? And because we're not a processor, we're not doing any housekeeping operations, we're not doing any other sort of instruction processing. We're only doing exactly what your model needs done, nothing more and nothing less. And so when you have a solution like this, you could call it hyper specialized, right? Where only your model is being executed, and so you have all the efficiencies of a single purpose circuit, right? Now the other one, where we talk about in the middle there, an unbounded parallel implementation, what that essentially means is that you can apply the circuit form to any number of input streams. So you can achieve, theoretically, limitless frames per second. So if you need multiple sensors coming into the circuit, you can do that as well. It's just a matter of designing more input channels. So you begin to be able to approach a truly sensor fusion solution by being able to run, say, the same model across a number of circuits. And then finally, the third patent extends the circuit approach not just to 2D images, but also to 3D. And when you look at a three-dimensional scale, that scale can be spatial, or it can be time or temporal. And so you can use time as a third dimension. And we have a patent on that because the circuit form simplifies the mathematics in that particular calculation that is unique. And from what we understand from the patent office, there is nobody in the world, there is not another single patent that comes anywhere close to putting machine learning algorithms into a circuit. So we're the only one in the world that's doing this sort of work. Okay, next slide is just a slide here showing some of the benchmark testing that we've done, where on the right we've taken a popular set of GPUs. Probably the most capable there is the A100, and we used a SqueezeNet convolutional neural net model. It's about an 18-layer model, and we fed the model at 240 frames per second and a high definition image, so 1920 by 1080. So quite a heavy workload. And as you can see there, a very powerful GPU at A100 was running at about 28 frames per second and a clock rate of over 1400 megahertz. And then, of course, it turned in a latency of 41 milliseconds. For us, we just ran on a normal Xilinx FPGA, field programmable gate array, at about half the clock rate that FPGA is capable of, so at about 125 megahertz. And again, the performance is deterministic, right? So we ran at exactly the frame rate that the sensor was feeding our circuit, and the latency there measured really in microseconds rather than milliseconds. So really an impressive result. We did the same for a ResNet 34, and in this test, what we tried to show is the unbounded performance, right? So however many frame rate speed that you need in your computer vision model, you can design a circuit to perform to that level. So whether it be 1200 by 1200 or whether it be HD or 4K, it doesn't matter what that workload is, the performance is deterministic, and you scale out, right? So if you need more frames per second, you go from what we call a 4 up or 4 pixels ingested at a time to 8 pixels. It could be 16 pixels, it could be 32, whatever you determine. However fast you need your machine learning model to run. Okay, so just a word on computer vision and a unique capability that comes out of the circuit form. And in this case, we call it unlimited recognition. So if you're familiar with computer vision, you'll know that a popular model like YOLO has to make a determination or split up the frame into a number of grids to examine each object class within that grid. And then it has to determine which ones are most confident. That's quite a calculation to make, right? And so in most cases, it's limited in only identifying 3 or 4, maybe up to 5 objects in that grid in order to make that determination. So it loses a lot of objects in the image, in the frame. And it's limited especially when you're looking at small objects and groups of small objects, because as you can imagine, and as you see here in the yellow box, you're trying to make a determination of a bounding box around a very small object, and you get a very crowded grid. For our circuit form of computer vision, we can take that same YOLO model, but simultaneously apply it to the entire frame. And so now you don't need to divide the frame up in grids, and you don't need to do those repetitive calculations in order to split up the grid into smaller models, or excuse me, smaller frames, so that you've got a workload that you can handle. Not so in a circuit form. And so what we say is you can identify an unlimited number of objects of every trained class in your frame. And there clearly is no other solution that we're aware of in the entire ecosystem of machine learning that can make that claim. So it's quite an astounding claim that we make, but certainly give you the opportunity, or give you the advantage of, let's say, in a fast-moving battlefield operation where you've got a lot of small drones that might be moving in on your position. You'd be able to capture every one of them and to be able to characterize their movement and to be able to address that threat far, far more quickly than you would be using any conventional approach, using any sort of von Neumann architecture. So quite an astounding result occurs with a circuit form. So just doing some operational examples now, how can you extend that, and what does that mean? Well, on the right, using a state-of-the-art GPU, right, at about 28 frames per second against a high-definition image, you're going to be able to look at something like a Hellfire missile traveling at, say, the speed of sound, maybe just above it. You'll be able to sample that and look at that missile once every 50 feet of its flight. Using our unbounded capability, you could dial or have any frame rate that you want. And here, as an example, we're using 1920 frames per second. So you theoretically could look at that missile every 9 inches of its flight path. And from a statistical standpoint, you're going to be more accurate in identifying that. But what's also interesting is that in the circuit form, you don't need to train accuracy for speed, right? So if you want greater speed, typically what happens is you're going to reduce your accuracy a little bit in order to reduce the workload. And that way, that'll make you faster. But in the circuit form, where everything is hardwired into the silicon fabric, you don't need to do that trade-off. What you can do is right-size the precision and include the precision as high as what you may need, so that your model is absolutely as accurate as it possibly can be. And critically, what that does is it reduces the false positives that might occur in an operational application. And those false positives can be deadly, right? So if you're a user and you're using a machine learning solution and you see a false positive, it's going to take some of your cognitive workload to resolve that false positive before you move on to the next target. And in fact, that distraction could be deadly. And so here we're saying that the computational power that a circuit form gives you is you can really reduce those false positives and increase the model accuracy to as accurate as you can possibly design it. Okay, so the next question you might have is, all right, understand all these benefits. How do we integrate it into my solution? Well, integrating it is, one part is fairly easy. The other part, it could be disruptive. So any machine learning engineer can give us their model. We'll take their model and we'll build a circuit generator, an automated circuit generator. That might take us a month or two. But once that automated circuit generator is created, we can kick out circuits in 24 hours. If your model is very, very complex, it might take even a day or two to kick out that circuit. But what happens is that circuit generator will build a circuit in the form of a bit stream. That bit stream can be loaded onto a FPGA, a field programmable gate array, just like any other bit stream is loaded on that gate array. And your user will not see any difference in the result than he or she would have seen from a GPU. It'll be exactly the same, except it'll just be orders of magnitude faster. And what might also occur is we can hardwire the weights into the circuit for optimal performance. Or if you're in a situation where you think your weights might change because you're retraining that model, well, then we can make the weights dynamic, and that would just be something that you would load up when you boot up the hardware. So there's a static set of weights, or you can make a dynamic weights. But give us the model, we'll kick you out a bit stream, you load it into an FPGA, and away you go. Okay. Now, the one thing I will say, though, is if your model is so complex and your performance target is so high, it may in fact be more than one FPGA. And in that case, we would advocate moving to an ASIC. And an ASIC is certainly the optimal form of any circuit. Okay, really quickly, last slide, second to last slide here. What is it that, or who have we been talking to? One of the first guys we spoke to is the Army Atlas program. They're trying to do target recognition, classification, and tracking. What we're allowing them to do is explore higher resolution cameras, to be able to explore more complex algorithms, because now they have the computational capability to do it. That higher resolution camera can see the smaller objects, such as drones and so forth. And then with our unlimited recognition capability, they're able to identify every drone in a frame. The guys at the Naval Surface Warfare Center are doing essentially the exact same thing, but they're adding tracking to the solution. They want to be able to track targets and help reduce the cognitive workload of a Marine inside of an armored vehicle, where they can prioritize what object is presenting itself as a threat. We've also talked to the F-22 program office. They have an infrared system that's a generation behind. Using our capability, they're able to have a more robust computer vision model, which allows us to help them increase the capability of that. And so in coordination with the Air Force Research Lab, we're exploring different platforms that we can put our circuit form on. So quite a bit of claims here. Happy to to dive into this deeper offline, but really appreciate the opportunity to talk to you all. And of course, any of our results, we just say are guaranteed. And we'll stand by that. And my contact information is there. So again, very thankful and grateful to be able to talk to you all. Thank you.
Thank you very much, Joseph, and thank you everyone in the audience for tuning into this session. We will go ahead and take a 5-minute break, and then we will hop to our next presentation. Thank you all.
Thank you, Cole.